In chemistry, it's important to distinguish between thermodynamics and kinetics. For example, if we think about the conversion of carbon as a solid in the diamond form to carbon as a solid in the graphite form, thermodynamics tells us what will happen. Will this conversion happen at a specific temperature? Whereas kinetics tells us when the conversion could happen. Let's start with thermodynamics. We can calculate if this conversion will happen at room temperature of 25 degrees Celsius by calculating the standard change in free energy for this reaction at that temperature. To calculate the standard change in free energy for this reaction, we need to know the standard change in free energy of formation of the products, and from that we subtract the standard change in free energy of formation of the reactants. For this conversion, our product is carbon in the graphite form. And because carbon in the graphite form is the most stable elemental form of carbon at a pressure of 1 atmosphere, the standard change in free energy of formation of carbon in the graphite form is equal to 0. Next, we think about our reactant, which is carbon in the form of diamond. The standard change in free energy of formation of carbon in the diamond form is 2.84 kilojoules per mole. Looking at our balanced equation for this conversion, we're converting 1 mole of diamond into 1 mole of graphite. Since there's a 1 as a coefficient in front of diamond, we multiply the standard change in free energy of formation of diamond by 1 mole of diamond. Moles cancel, and we get negative 2.84 kilojoules as the standard change in free energy for this reaction. Instead of kilojoules, the units could have been written as kilojoules per mole of reaction. Because there's 1 mole of carbon in the diamond form for how the balanced equation is written, we could write a conversion factor of 1 mole of carbon in the diamond form per mole of reaction. And because the standard change in free energy of formation of diamond is equal to 2.84 kilojoules per mole of diamond, moles of diamond would cancel out and give kilojoules per mole of reaction as the units. Because the standard change in free energy for this reaction is negative, we know that the conversion of diamond into graphite at 25 degrees Celsius is thermodynamically favorable. Next, let's think about the kinetics of this reaction. If we look at the structure of diamond, each carbon atom is covalently bonded to 4 other carbons. For example, this carbon right here is bonded to 4 other carbon atoms in a tetrahedral geometry around this central carbon atom. Graphite has a very different structure. In graphite, carbon atoms form covalently bonded layers or sheets, and these layers or sheets are held together by London dispersion forces. So in order to convert diamond into graphite, we would have to break a lot of carbon-carbon bonds, and that would take a lot of energy. Since it takes a lot of energy to break the carbon-carbon bonds in diamond, if we look at the energy profile for this reaction would have a very high activation energy, symbolized by EA. And the higher the activation energy for the reaction, the slower the rate of the reaction. At room temperature, it's estimated this reaction could take billions of years. Therefore, we would say this reaction is kinetically unfavorable. Finally, let's summarize what we've learned about the conversion of diamond into graphite. Thermodynamics answers the question, will the reaction go? And the answer to that question is yes, at room temperature, diamond will convert into graphite because delta G naught for the reaction was negative. Kinetics answers the question, how long will it take? And the answer to that question is, it would take billions of years for diamond to turn into graphite at room temperature. The reason why the reaction is so slow is because of the extremely high activation energy. So even though the reaction is thermodynamically favorable at room temperature, because the reaction is so slow, the reaction is kinetically unfavored, and for all practical purposes, the reaction doesn't happen.